I plan to review some concepts from 2.11 since it's been a couple of years since you've seen that. There's a few things from that course that are sort of foundational to this course, so I'm going to cover those. And then I'm going to introduce SystemVerilog, which is the language we're using in this class, and it's the language that you'll use for the first lab assignment. So first thing is logic gates. I'm sure you all remember logic gates from 2.11. Logic gates are digital electronic circuits. Electronic means that they're built with transistors, and digital means that they're designed to process digital signals which have discrete voltage levels. So generally there's a low voltage and a high voltage representing 0 and 1 or false and true. Logic gates have one output. They can have multiple inputs, but they have one output. So for instance, like for an inverter has one input, one output. It performs the Boolean complement operation, and it has the truth table that just has 2 rows because there's only one input. There's 2 to the first power rows in the truth table. Buffers are just the identity, the Boolean identity function. Buffers show up generally whenever you need like an amplifier or a driver in a circuit. You all remember that stuff? Okay. There's 2 input logic gates. There's the, for example, and or perform the Boolean and or operations. These ones have 2 inputs. They can have more than 2 inputs though. Because these have 2 inputs, they have 2 to the second power or 4 rows in their truth tables. And is true whenever both of its inputs are true and false otherwise. And or is false when both of its inputs are false and true otherwise. Now, these are kind of classical gates, but I mean, in truth, you could have, you can build a gate, an arbitrary gate, however you want, at least conceptually. So if you have a logic gate with 2 inputs, how many possible gates could you build from that? Anyone know? Had this as a test question last year in this class. So if you have 2 inputs, how many possible ways, how many possible gates? Well, there would be, so there's if you have 2 inputs, there's 2 to the second power rows in the truth table, right? Now, the gate is defined by the output column, right? So the output column has 4 entries in it, so there's 2 to the 4th power possible ways you can configure this thing, right? So if you think of the output column as a 4-bit number, then there's 16 4-bit numbers that you could put in there, right? So in general, if you have n inputs, then there's 2 raised to the 2 raised to the n power possible gates that you can build from that, right? 2 to the 2 to the n, right? That's how many gates. Now, these gates, usually when you see a logic gate, you think of that being built with transistors on an ASIC, on a semiconductor chip. But I mentioned last time that on an FPGA, these gates are built using LUTs, lookup tables. So on an FPGA, these lookup tables are actually created in a RAM, in a 1-bit wide RAM, right? And the depth isn't 4, but is actually, there's 7 inputs on modern FPGA LUTs. So there's 2 to the 7th power entries in this RAM that comprise the truth table. So there's 128 entries. So an FPGA is comprised of a C of 128 by 1 RAMs, 128 entries deep by 1 entry wide that comprise these logic gates. And when you fill those RAMs in, you're filling in the truth table, and you can make any kind of gate you want, right? Now these and OR gates are just, these define the specific truth tables for these guys. But you could put any value in this output column on an FPGA and get, kind of a reconfigurable general purpose logic gate, right? You guys with me? It makes sense? So a LUT can be built into 2 raised to the 2 raised to the 7th power possible gates. So 2 to the 128th power. That's a big number, astronomically big number. And that's just one LUT on an FPGA. Those are possible gates you can build from that. Now, one of the things I taught last year, I'm not going to cover it this year, but when you build these in CMOS, if you were to make an ASIC, instead of using a LUT, if you wanted to build one of these with transistors, and you're using CMOS logic, which is how all modern chips are built, you can't actually build an AND gate because CMOS is negative logic. You have to have at least 1 0 in the row that pulls the value up to 1. There has to be at least 1 0 in there in order to build this gate out of CMOS logic. So if you need an AND gate in a real chip that you're making, you just use a NAND gate followed by an inverter. But anyway, okay. So then there's other kind of gates. You guys probably remember XOR, NAND, NOR, XNOR. These are different truth tables, different Boolean operations. You can also scale these up to multiple inputs. So a 3-input NOR gate would be true only if all the inputs are false, right? And false otherwise. So think of it's basically a 3-input OR followed by a complement, right? 3-input AND gate would be true only if all the inputs were true, all 3 inputs were true. Okay, you guys with me? So again, you can build these in a LUT on an FPGA, or if you build them on a custom chip, then you're building them with transistors. And in that case, you can't. There's some limitations on which gates you can build in CMOS logic. Okay, but not in a LUT. You can fill LUT in with whatever you want. Okay, so I mentioned logic gates only have 1 output. What if I need more than 1 output? So logic gates are used to build logic circuits, which are more abstracted designs, right? So a logic circuit has a set of inputs, 1 or more inputs. It can have 1 or more outputs, unlike a gate that just has 1 output. And then there's a functional specification. This is the important thing for this class. The functional specification is what we're writing in Verilog, or SystemVerilog, rather, sorry. So now in a, you can define the function with Boolean logic or a finite state machine, if it's sequential logic, or like I said, in this class, we're using a high-level language to define the functional specification. That's basically just what it does. And then there's a timing specification which defines the timing, the constraints of the input, the timing of the input signals, as well as the timing of the outputs. And we'll get into that a little bit in another lecture. Today, we're just going to focus mostly on how to define the functional specification. Now, when you drill down inside of a logic circuit, so this slide is showing it sort of as a black box. So you can see the inputs, the outputs, you know what it does, you know how it performs, how the timing, and what the sort of the timing constraints are. How long it takes for outputs to change whenever you change an input, for instance. That's part of the timing specification. But this is the information that you would give to a user who wanted to use your logic circuit. This is kind of an interface spec. For you to design a logic circuit, you have to sort of think of it like, like drilling down inside and opening up the hood and what's inside. Inside a logic circuit, you have logic elements that are generally logic gates or LUTs. There's these elements in here. And then they're connected both to the inputs and outputs, as well as, in some cases, to internal wires that are not visible outside the circuit, but when you go inside, you have these internal wires that make connections internally. This is kind of like, if you think of an object-oriented language, I like to think of this, these are kind of like private members in a class, sort of. So they're not visible outside, but they're inside. Now you might say, wait a second, hold on. There's more than, you've got one internal wire labeled N1, but there's other internal wires in there, right? Why aren't they labeled?
They're outputs.
Yeah, the other wires are actually, the other wires inside are actually connected. It's kind of hard to see, but all of the wires in here are connected to either an input or an output, except for this one. N1 is the only one that's just internal, right? So for instance, A is an input that comes in and it kind of tees off. This is a fan out. It fans out, where A connects to E1 and then it splits and also connects to E2. So this is actually, both of these connections, the E1 and E2, come from A. And then B also splits off, connects to E1 and E3, right? And then E2 has an output that's connected to output Z, but then that output also splits off and is used as an input to E3. You guys all see that? Yes?
Why are the fans up from A goes over top of E2? Is that a hop or is that just like?
Yeah, I'm going to get to that. This part's a little confusing. This is a convention that's used with block. This is a block diagram or a schematic. Yeah. In the textbook that we're using in the class, if you have a crossing like this, they're not connected. If you have a crossing like this, there would have to be like a dot there to be connected. Now, what confuses me sometimes is that, well, wait a minute, hold on. What about this connection, this T connection? There's no dot there, but yet A is shorted. This is a connection where it T's, but this is not a connection where it crosses. So I still to this day sometimes I get thrown off by that. So a T connection is connected, a cross is not, unless there's a dot. That's a good question. There's a slide here that addresses that too. Okay, there's two types of logic circuits, and I think this is where, I don't think our 211 course covers this very thoroughly. I think they might introduce this. There are combinational logic circuits and sequential logic circuits. The difference is combinational logic has no memory. What that means is that the outputs of a combinational logic circuit are just a function of only the inputs. Whereas in a sequential logic circuit, it has memory, and so the outputs are a function of the inputs, but also of the input history. So they remember the history of inputs, or the recent history of inputs, and they use that together with the current input to calculate the output, or to determine the output. We will cover both in this class. My intention was to start with combinational logic, and then in the next lecture I'll get into actually in 2 lectures from now I'll get into sequential logic, but I have to cover some sequential logic in this lecture because it's really impossible to do a lab in SystemVerilog without putting some sequential logic in. You can't go to an FPGA and build a purely combinational logic circuit. It's impossible. So I am gonna cover some sequential logic today, but I'm not gonna get into it. I'm kind of gonna gloss through some of it. I'm just going to try to cover enough just to get you through Lab 1. And then I'll give a more formal treatment of sequential logic in 2 lectures from now. Okay. Okay. In combinational logic, there's some rules. Every node, so every element is combinational, basically meaning every element is a gate as opposed to a flip-flop, right? So these are, or RAMs. So these are just gates in here in combinational logic. Every node is either an input. So you can have these input nodes that are actually input ports. You can think of them or input pins, or it connects to exactly one output. So what that means is you're either a pin, you're either an input pin, or you're a gate. And if you're a gate, you can only have one output, as I mentioned earlier. And the circuit contains no cycles, because when you put cycles in, you potentially create a sequential circuit. Or you can create something that's not stable, like an oscillator, right? But in combinational logic, there's no cycles. Okay, so what about the functional specification? I mentioned this earlier. You could think of the functional spec as being a Boolean logic expression, right? Now you can see that the Boolean logic here has an equal sign, an assignment. There's a right-hand side that's the inputs, and the left-hand side is the output, right? So S is an output, C out is an output. They appear on the left-hand side, A, B, and Cn are inputs. They appear on the right-hand side. And in this case, S is A XOR B XOR C, right, in Boolean logic, right? So that's one way to specify the function. So I want to quickly, I'm going to go through this stuff kind of fast, this Boolean stuff, but if anyone has any questions, please feel free to stop me. So just to review some terminology, there's a complement means that you have a variable. The variables are inputs and outputs. The variable, if you put a bar over it, or sometimes you can put like a turned L to the left of it. There's different notation, but in this book they use a bar for complement. This is the logical complement. I sometimes call it negation, which I think is technically wrong, but it's a bad habit I picked up. So sometimes I'll say negate or complement. It means, you know, take true as false and make true false and make false true. A literal is a variable or its complement. So A and A bar are both literals. An implicate is a product of literals. And product, when they say product, what they mean is literals that are ANDed together. Now, what is it called if you have literals that are ORed together? Not a max term, because a max term requires you to have all the variables, all the inputs, right? Min-term and max term are when you have, if you have an expression of 3 inputs, you have to have all the inputs in the min-term or max term, right? An implicate is min-terms are implicates, but implicates are not max terms. Implicates don't have to have it doesn't have to have a literal corresponding to each variable, right? So that's an implicate. I'm not sure what the opposite of implicate is. But anyway, implicate, yeah, is when you AND together. It's the products of literals. Okay. And as I mentioned, min-term and max terms are a product that includes all the input variables. Right. So you have a literal corresponding to each of the variables in a min-term and in a max term. Okay, then there's sum of products form, which is a canonical form where you're specifying the functional behavior of a logic circuit, or it's a Boolean expression that's comprised of, well, sum of products. Technically, you just need the implicates, but in this case, if you have a truth table, and your goal is to take that truth table and represent it as an expression, a Boolean expression, then you can go through the truth table and find each row where you have a true output, and you can convert that to a min-term by you construct a min-term for each row by having a complemented variable corresponding to each of the zeros in that row, and a non-complemented variable corresponding to each of the ones, right? So in this case, going from the top to the bottom, the first one I see in the output column has A is 0 and B is 1, and so my corresponding min-term for that row is not A and B, right? Which is min-term 1. And the reason it's min-term 1 is because if you look at the inputs that correspond to that, it forms the binary value 1, right? And then there's another one here where A is 1 and B is 1, and the min-term is A and B. That is min-term 3 because that's 3, right? And so if I take those min-terms and I OR them together, I get the sum of products representation of that. Now, one thing you have to understand about this is the tools we use in the class, the CAD software, CAD, computer-aided design, or sometimes it's called EDA, electronic design automation. The tools do not do this because, generally speaking, if you have any logic circuit of any non-trivial size, will give you a truth table that's way too big to do this with. This really only works on kind of small toy problems, right? Generally speaking, in the tools that we use, they process. There's a synthesis phase I talked about last lecture that does iterative transformations to Boolean logic. right? So it has a Boolean logic and it tries to minimize it by doing Boolean operations. It doesn't ever try to generate the whole truth table, right? Because that would grow too fast. You guys with me? But if you have the truth table, this is a way that you can go through it and construct a Boolean expression. You guys with me? Right? So I guess what I'm trying to say is, I don't think I explained that very well, but when you write code in Verilog, SystemVerilog, or VHDL, or any of the HDL languages, generally speaking, the compiler for that is converting your code into Boolean. And then it processes that Boolean using heuristics that try to minimize the logic or map the logic. I gave you an example of mapping last time, right? But that's done in Boolean, right? Boolean expressions. It never generates a whole truth table. That's not practical. Okay. Right, so anyway, the sum of products is, in this case, this truth table would give you not A and B or A and B, right? So this is, like I said, this is good for test questions, but it's not what the actual tools use. There's also product of sum product of sums, which is where if you take this and you apply De Morgan's law to it. You guys remember De Morgan's law? That's something I covered. I'm not going to cover that this time because I assume you guys had that, and you should have covered that pretty well in 211. But if you do De Morgan's law, it'll convert the sum of products into product of sums, right? So another way to do this is, instead of finding the rows with a 1 output, you can find the rows with a 0 output and construct the product of sums for those rows, and then you do De Morgan's law, and it converts it into sum of products. Because the idea is, if you construct an expression that gives you the false outputs, then what you're really looking for is the true output. So you apply De Morgan's law, right? Another way to do that is to just take these rows with a 0 output and negate each of these guys. So if you have A0 and B0, then you create a max term that's A or B, right? Now notice there's no complement over A or B, even though these guys were both 0, because this is the De Morgan's law part of it, right? You take the individual variables and you complement those, and then you build a max term, and you're doing this for the rows with zeros. Does it make sense? So in this case, this is A or B and A. Oh, that's screwed up. Let me fix that before I forget. I fix that. This should be, which one's complemented? This would be the B. Yeah, there we go. Wait, let me move that up here. Formatting got screwed up. There we go. See that? So notice that it's A is 1. Oh no, sorry. No, I put over the wrong one. That should be over the A. It's a good. This actually was fortuitous. A is negated, right? Why? Because here A was 1, right? So what I'm saying is, when you construct the min terms are matched right up against the logical values of the input in the rows that you're making the min terms for. For the max terms, you just switch it. So the max terms is, you find the rows with 0 outputs, you construct your max terms, but you complement each of the individual variables, right? So this is why you have A and B are both non-complemented here in the first max term, and in the second max term, you're complementing A and you're not complementing B. You guys see that? Okay. Okay, so this is a little cute example. You're going to the cafeteria for lunch. You won't eat lunch if it's not open or if they serve corn dogs. So basically, E is going to be 0 or false if O is false or if C is true, right? So if O is true, if O is false, right? If it's not open, so that takes care of these two rows, right? Because if O is 0, then I'm not going to eat lunch. And if they only serve corn dogs, if C is 1, which is this row, then we're not going to eat lunch. The only way we're eating lunch is if it's open and they're not, if they're not only serving corn dogs. Make sense? Okay. Okay, so so if we take that truth table, we can calculate a minterm, which is O and not C, which is minterm 2, 2 being the 1, 0 is 2 in binary. And then if we do max terms, then we've got 3 max terms because we have 3 rows that produce a false output. And this is where it's a little confusing because we have to negate the individual input. So in this case, we have a 0, 0, so we have a OC. A 0, 1 is going to be a O not C, right? And a 1, 1 is going to be a not O or not C. Okay. Okay. Any questions about that? Okay. Okay, so this is the thing I mentioned earlier, the circuit schematic rules. So wires, if you have a circuit schematic, and we're going to have a lot of these because a lot of times you'll have designs in schematic form and then you have to convert them to Verilog. You have to sort of transcribe them into a high-level language, an HDL. In the past, when I first started teaching this class years ago, we had I used to use a schematic capture tool where you could actually draw schematics and then you'd hit a button and it would generate the HDL for you, right? And that was fine. I mean, it was a good way to learn, but that wasn't ideal because in the years that went by, and I started working with industry, I realized that no one uses those tools in industry. No serious computer engineer does that. That's like training wheels. So I changed the class to where we write code, right? So, but what that means is that in a lot of cases, I'm going to be giving you schematics that form the design of a CPU, and you're going to have to go through those schematics and convert them to text, right? It's kind of like if I give you a mock-up for a website and then had you write it in HTML, right? It's similar to that, right? So that's why we have to understand how these schematics work. You have to be able to read these schematics. So anyway, as I mentioned, yeah, if you have a T-junction, the wires are connected. If they cross, you need a dot for them to be connected. If they cross without a dot, then they're not connected. Okay? All right. Okay, so here's an example of a, let's see, I think we just have one example of this. Yeah, okay, so let's consider this priority encoder. Actually, this is a priority decoder? Encoder? I don't know. It says it's priority circuit is what they call it. So there's 4 inputs, and the idea is that you want to have the output is going to be all zeros if all the inputs are zeros. And otherwise, we want to have a 1 in the position of that corresponds to the most significant 1 in the inputs. That was a horrible explanation. But basically what it means is if you have all zeros in the input, you have all zeros in the output. If you have a 1, if the most significant 1 in the input occurs in bit position 0, then I'm going to light up bit position 0 in the output, right? This is a decoder in the sense that the output is 1 hot, or it's a unary output, right? In the sense that, generally speaking, only one of the output bits is 1, right? So it's going to correspond to whatever the most significant bit in the input is. So in this case, if I have a 0, I put out all zeros. If I have a 1, I'll have a 1 there in bit position 0. If I have a 2 in the input or a 3, in both values, I've got a 1, in the most significant one in the input is in bit position 1, so I light up bit position 1, right? Make sense? And then likewise, if I have 4, 5, 6, or 7, I will light up bit position 2 because that's where the most significant 1 bit was in the input. And in the other 8 cases, if I have 8 to 15 on the input, then I'll light up bit 3. You guys with me? Okay. Okay. So what does this do? I mean, who would ever use something like this? Well, this is actually pretty common. It's a priority circuit. It's like if you have, say, a router, and you have 2 inputs come into your router, and they're both destined. They both want to go to the same output, right? I should say not router, crossbar switch, whatever you want to call it, right? The idea is you have inputs and outputs, and you want to be able to route the inputs to the outputs. Whenever you have a contention, you have a conflict, you resolve it through, this would resolve it through a fixed priority, meaning that, for example, if I have 2 inputs coming in, 1 and 0 both want to go to the output, then I resolve it by giving the, I arbitrate and allow bit position 1, the number 1 to go, right? Right, so this is it's a priority circuit. Okay, so one way you can build something like this is you can convert it to gates, where if the third bit 3 of the input is asserted, that would be connected directly to Y3. And then you have Y2 is going to be not A3 and A2, right? And you might say, where are you getting the not A3? There's a bubble here on the input that is complementing the A3 input into this gate. All right, you guys with me? So the only way Y2 can be asserted is if A3 has to be 0 and A2 has to be 1, right? So that means if you look at the truth table, we're dealing with these 4 rows, and in these 4 rows, you have a 0, 1, right, for A3 and A2, right? Now you might say, well, wait a minute, that's not a full, that's like a minimized version, because these guys are not max terms, right? Or this is not a canonical form at all, right? But the way this was constructed was by using don't care. So a don't care can either be in the input or the output. This used to confuse me when I was first learning this stuff. So you guys probably, in 211, you probably talked about don't cares, right? And if you have a don't care in the output, that means I don't care what the output is. And so I can use that to my advantage when I'm trying to minimize a circuit with a Carnot map, right? But in this case, this is different. I don't know if you guys addressed this in 211. These are don't cares that are in the inputs. This is different. So in the input, it's like saying I don't care what that input is, right? So that don't care in the input is like a shorthand way to have one row in a truth table that actually expands to multiple rows if you had every possible input combination. Make sense? So in that logic diagram I showed you in the schematic, basically the way they did that was notice that the A3 was connected directly to the Y1 because you had a 1 there, and then there's the 0, 1 that corresponded to this gate, and then there was a 0, 0, 1 that corresponded to Y1. Right, so there's a 0, 0, 1. You see how they built that? So they took advantage of the don't cares. Now you can have don't cares as inputs or outputs in Verilog, and we'll talk more about that in a bit. Any questions about that? Okay. Okay. Now one of the things I don't like about Verilog is they have this variables can be 0 or 1, obviously, but there's a couple additional values that you can have assigned to a wire. One of those values is x. The problem is that X has two meanings. If you specify X in your code, that means it's a don't care, right? So you can assign something as X, in which case you're telling the synthesizer you want it to use that to minimize the circuit, right, to optimize the circuit. You can also, in some cases, use that as an input, too, in case statements, which I'll cover here in a minute. But that's generally is you can type in X, and it means don't care. However, when you're simulating your code, and you see an X, that doesn't mean don't care. That means that's bad. That means there's a problem. Generally, what it means is there's contention. Now, remember, I don't know if I had this in an earlier slide, but every net, a net being like a node, think of it like in Spice, you have a node. Every wire, every variable can only be driven by one driver, one gate, right? So you have to be careful when you write Verilog, and I'll get into more detail about this, but keep in mind that you cannot have more than one circuit connected to the same wire for its output. If you do that, and if one of the two circuits tries to set it to 1 and the other one tries to set it to 0, what's happening there is in the circuit, you've got one gate that's trying to pull the voltage up, and the other one's trying to pull the voltage down, meaning you've got one gate that's trying to short that wire to VDD, and the other one that's trying to short that wire to ground. And so if you were building a circuit that did that, it would short out, basically. You'd have a low impedance path between power and ground, and generally speaking, it'll heat up and burn up, right? It lets the magic smoke out, like Charles would say.
Smoke check.
Yeah. But luckily for us, we don't have to worry about that because you can't do that in this class because the tools will detect that. The compiler won't let you do that. It won't let you short the FPGA out. So you don't have to worry about like writing code that causes a short circuit and then blowing up one of the FPGAs. It's not possible.
Well, in theory, it's digital, so we couldn't actually make it do that, right?
No, you could. You could have two assignment statements that both connect to the same output, but you'll get an error when you go to compile it, right? So you'll get an error. When you go to synthesize it, you'll get an error. If you're simulating it, you'll get an X in the simulation window. So if you see an X, that usually means you're double driving something. I think that's everything that's in that slide. So just to summarize one more time, X in your code means don't care. X in the simulation means it's short-circuited. There's another special value, Z, which means floating. If you assign a value to Z in Verilog, it means that you're disconnecting it from both power and ground, from both 0 and 1, right? So this is used for Tristate buffers, for instance. That's one of these, looks like a buffer symbol with a little input at the top. This is the way that you get around the problem of double driving. So if you have, like, say, a shared bus, right? You want more than one bus master, and you're only going to connect one bus master at a time, you can do it through one of these tri-state buffers where you can turn off the connection between the input and the output, right? And the way that's written in Verilog is through this Z value. You guys with me? So for instance, if E is 0, which covers the first 2 rows of this truth table, because E is shown here as the most significant input, then Y is Z, meaning that E being 0 turns this tri-state off. And if E is 1, then it will just simply take whatever's coming in as A and connect it to Y, meaning that Y will be whatever value that is on A. You guys with me? Okay.
I got a question.
Yes?
What do you mean here by a node is floating?
Floating means it's not being pulled down. Usually in a digital logic circuit, every wire is either being pulled down or pulled up. It's either being connected to it's either in a 0 state or a 1 state, meaning that it's either VDD or ground, or something close to VDD and ground, right? So if you're when I say VDD, I'm talking about whatever voltage you're operating your chip at. So generally speaking, these days VDD is a volt. or on most modern chips, it's 1 volt. So, 1 volt means true, something close to 0 volts means false or 0. If something is floating, though, it's not connected to anything. So it's like an open circuit, basically. If you connect a voltmeter to it, it would give you some value between 0 and 1 volts, right? Although you won't know for sure by like as it mentions, you don't know for sure by measuring the voltage if it's floating. Make sense? Now the question is, can you do this on an FPGA? Can you do this can you disconnect a wire on an FPGA and make it floating? Yeah, you can actually. I've never done it though. I've never needed to do it. But you can actually you can put tri-states in Verilog and you can put that on an FPGA. I've never had to build anything that required that. I don't think, I might have. I don't know. I'm at that age now where I might have done it 25 years ago and just don't remember. But I don't have any recent memory of having to do that. But you can do it. And so here's an example where you have a bus. This is a shared bus. So you have a processor, video, Ethernet, and memory. These are kind of components that are all connected to a shared bus. And so in this case, this is a situation where I can take the processor and put something out on the bus, in which case I have to turn on its tri-state, right? Now the presumption here is that I only turn on one of these tri-states at a time, right? So there would be some kind of a, like that priority decoder that I showed earlier would be connected to these enables. And so I would only have one connected at a time. Likewise, I can use this bus for input as well. And so I have another tri-state going the opposite direction if I want to read something from the shared bus as opposed to writing to it. Everyone with me? Yeah, that's a tri-state, and again, that would be a Z. Okay, I'm sure you guys remember multiplexers, right? Should have covered those. Hopefully you covered those in 2.11. Multiplexers show up a lot in architecture. In fact, you might have noticed when you took 2.12, if you looked at any of those schematics in 2.12, there's multiplexers all over the place because that's the way that you route data through a processor is with multiplexers. That's how you establish data paths. That's how you drive data around inside of a microarchitecture, a processor design. So you're going to see these a lot. These are all over the place. You're going to be using multiplexers constantly. You're not actually putting a multiplexer down. You're writing the behavior of a multiplexer in Verilog, but it's still a multiplexer fundamentally. So a multiplexer is just to review a bit, it is a component that has multiple inputs, usually a power of 2. It doesn't have to be a power of 2. And then a single output, and then there's a select. The select, now the inputs can be 1 bit or multiple bits, but the inputs and the output are the same bit width. So like in a 32-bit processor, you'll see a lot of multiplexers that are have each input will be 32 bits and the output will be 32 bits, right? But they'll be grouped together as one line inside the schematic. You guys with me? And then it has a select where the select is the number of bits of the select is the log base 2 of the number of inputs. So if you have 2 inputs, there's a 1-bit select, right? Because you take the log base 2 of 2, you get 1. And the select is what you use to connect a specified input to the output. When I say connect, I mean kind of, think of it like short it, connect it, right? So here's the truth table of a 2-input mux where each of the inputs and the output are 1 bit each. The select is also 1 bit. And so together, these 3 inputs give you an 8-row truth table. So if the select is 0, which covers the first 4 rows, because the select input is shown here as the most significant bit in the input, then y will be whatever D0 is. So if D0 is 0, Y is 0, if D0 is 1, right? So if you look at the top 4 rows of this truth table, so I'm just covering up the bottom 4 rows. In the top 4 rows, D1 is a don't care, is treated as a don't care. I don't care what D1 is because I just take D0 and I make Y to be whatever D0 is. So Y and D0 are the same. If I cover up the top 4 rows, then I'm left with just the rows where the select is 1, in which case D0 is the don't care, and I just connect D1, whatever D1 is what is going to appear on the output, right? So this is a fundamental element that you use to route, to steer data around. This is how you can have multiple inputs that can go to one output. Now let me give you an example of when you use this. If you have a MIPS processor and you have an add instruction, I want to add 2 numbers and I want to put the result in the register file. But if I do a load instruction, I want to pull something from memory and put that in the register file, right? So I have these 2 values that I potentially may want to put in the register file. So you're going to drop a mux in there in front of the register file that will allow you to select what you want to write into the register file, right? The ALU, for instance, allows me to add the contents of 2 registers, or I can add the contents of 1 register with an immediate value, right? So that would be another mux I drop in there to select between whether I want to add 2 registers or 1 register in the immediate, right? There's options, right? So this is essentially a hardware if statement. Is what a multiplexer is, a hardware version of if in a programming language. So as you might imagine, they come up a lot because anytime you have any kind of conditional behavior, you have a mux in there, right? Make sense? This is an alternative form of the truth table too. Notice that they simplified it where they eliminated the D0 and D1 columns and they just have S. And if S is 0, then Y is just set to Z0. So they use this shorthand notation here. So this version of the truth table is the same as this one. This is the shorthand version. I could have also did another shorthand version where I put don't cares in there. Like I mentioned, like if S is, these 4 rows could have been reduced to just 2 rows if I would have used a don't care for D1, right, for instance. Any questions? Okay. Okay. Multiplexers can be built in various ways. There's different ways you can do it. This is you can take the truth table and put it into a Carnot map and resolve it down to a simplified circuit. In this case, they're using tri-states instead. So in this case, you've got D0 and D1 are both potentially shorted to Y, but they both go through tri-states, and I've got S comes in and there's a bubble on this tri-state, not a bubble on this one, so these tri-states become mutually exclusive because if S is 0, I activate the first one and not the second one, and if S is 1, I activate the second one and not the first one, right? But these are 2 different approaches for building muxes. In reality, when you write a mux in Verilog, it's going to get converted to LUTs like everything else on the FPGA. How it does that, I don't know. I don't know how no one knows how that stuff works because it's a trade secret. It's built into their tooling, their compiler. But generally speaking, though, the way it works is it's an optimization problem, right? You have multiple ways to build a mux, to generate a mux, but you have to take into account the resource cost and the timing constraint. So it tries to find a good solution on the FPGA. Okay. You can also use a mux. This is kind of a neat thing where you can think of a mux. You could take a truth table and you can take the inputs to the truth table and make them the select on a mux, and then you can hardwire the inputs on the mux to 0 or 1. Of corresponding to the outputs in the truth table. So if you think of A and B as the select input, then each row on this truth table represents an input to the mux, right? And so then you just take the inputs A and B and you make that the select, and then you hardwire the inputs to either 0 or 1 as defined by the output, right? So in this case, 0, 0, 0, 1, I've got 0, 0, 0, 1. I'm sorry, yeah, 0, 0, 0, because that's that little upside down triangle is ground, 0, false. And then that little T is the VDD, 1, right? Okay, I'm gonna skip that. Okay, let's talk about decoders. You probably remember this too. Maybe, I don't know if they covered this really thoroughly in 211. A decoder, we already looked at kind of a version of a decoder, that priority circuit was kind of like a decoder. But a decoder, a classical decoder has n inputs and 2 to the nth power outputs. And a decoder essentially takes a binary signal and converts it into a unary signal, meaning, a binary value and converts it to a unary value. Meaning that you take the input and you treat it as a number, as a binary number, and then you set the corresponding output to 1, and all the other outputs become 0. So if I have A1 and A0 and I put 1, 0 in there, then the decoder looks at that as 2, right? So it'll take output 2. So there's a 1, 0, and it'll take output 2 and it'll assert that to 1. It'll make it true, and all the other inputs will be false. So this creates a one-hot encoded value where you have these outputs, and each one of these outputs they're all zeros except for one of the values, one of the variables is 1, right? And that variable is determined by the input. You guys with me? So in lab 1, we're going to ask you to create a decoder is the object of lab 1, but we're going to do a 7-segment decoder, a little different, where and I think you built one of these in 211. The idea is you take a 4-bit value 4-bit binary value that could be any of its 16 values, right, 0 to 15, and then you're going to decode those to not a 16-bit output, but a 7-bit output for a 7-segment display, right? So it's still a decoder in the sense that you have a smaller number of inputs are being converted to a larger number of outputs, right? You guys with me? Okay. So why do I bring this up? I bring this up because these types of behaviors are very common when you're doing HDL design. It comes up quite a bit. And this is a possible decoder implementation where you've got, you sort of set up a PAL type structure. PAL or PLA? PLA, programmable logic array thing, where they show it, where they've got the 2 input variables, and you've got the complemented form of them, and you're connecting them to this array of AND gates. So Y3 is going to be asserted when you've got A1 is true and A0 is true. Right? Make sense? Yeah. Right? So 1 and 1 gives you true on Y3, and then Y2 is A1 is true and A0 is false. If that was the case, and you get a Y2. Y2 is true, which is this row. Make sense? Okay, and then this is another kind of variation on if you have a decoder, and you can actually use the decoder to build an arbitrary logical function by using the inputs and sending them into the decoder, which will cause the decoder to light up one of the outputs corresponding to each of the 4 min terms, right? And then you can then feed those min terms into a big OR gate. You just connect all of the corresponding min terms into an OR gate, and you can create an arbitrary logic function this way. So the decoder never changes. The only thing you have to change to make this work for an arbitrary logic function is which of the outputs of the decoder you feed into this OR gate. You guys with me? Okay, so that is my brief review of 211. Any questions? You guys remember that stuff? A little bit. Okay, so now I'm going to switch gears here and talk about something totally new. This is I'm going to introduce hardware description language. It's kind of an interesting history. I don't have a lot of, I don't want to go into too much here. But originally, just to give you kind of a really brief history of this stuff, it all started in the, I think it was in the early 80s, late 70s, early 80s. The Department of Defense was starting to buy a lot of integrated circuits from military contractors to control stuff, weapons. And whenever they would order something from a contractor, they would have to describe the behavior of the chip in English prose, right? There was really no other way to do it. They'd have to they would literally write, a description in English of what the chip was supposed to do. But as you might imagine, that's a very imprecise way of doing it. And as the chips that they were ordering became more complex, there was a growing amount of ambiguity in the descriptions of what the military wanted these guys to make, right? So the first HDL was developed as a solution to this problem. The idea was to have a language that we could use as a specification language, a way to define the behavior of a circuit in a very precise way. And so that's when the first HDL was VHDL. VHDL was a nested acronym. VHDL stands for VISIC Hardware Description Language, and VISIC itself is an acronym that stands for Very High Speed Integrated Circuit. So Very High Speed Integrated Circuit, HDL. Very High Speed Integrated Circuit Hardware Description Language. So it was developed in 1981 by the DoD. Now the thing is, once we had this, it was like, well, wait a minute. What if if we compile this language, we can do stuff like write a simulator. So this way, if you give me a VHDL description of a circuit, I can essentially compile it and instantly get a virtual copy of the circuit, right? That I can play with, and I can run it in the simulator, and I can hit it with test vectors and manipulate the inputs and see what happens right away without having to do anything. I don't have to make anything. I can get instant virtual chip. But then they took it a step further and they said, wait a minute, because the original intent was the DoD would give you a VHDL file, and then you would have to design it by hand. You'd have to wire transistors together. But then it was like, well, why don't we just take the VHDL and compile it into a circuit, right? Then we don't have to make anything manually. And that was the birth of synthesis tools, synthesizers. So first came the simulators, and then came the synthesizers. We're going to use both in this class. We're going to have a simulation flow and a synthesis flow. The problem is that VHDL was based on Ada. Ada is a language that was derived from Pascal, and it was designed to be self-documenting. That was basically the idea of Ada. Ada has other advantages too, but one of the characteristics of Ada was that if you write code in Ada, you don't have to write comments for it because it's so verbose, you can just read it. It looks almost like English. Everything is spelled out. When you declare a variable, you have to type variable. And if you have an array, you have to say array 15 down to 0, range 15 down to 0. So everything is very verbose. And that's nice. It makes it readable. But it takes forever to type it. It's so wordy. So Verilog came out a few years later. So VHDL is kind of a government project. Verilog came from industry. Verilog looks closer to C. It's more efficient and it's more sparse, but it's impossible to read. So you better comment it, because it's you can have a little bit of Verilog, but it's not really clear on first glance what the heck it's doing, because it's not all spelled out. It's designed to be terse and concise, so you don't have to type as much, but you better comment it, because otherwise it'd be hard to read. So to this day, these languages share roughly 50% market share. So it's weird. 40 years later, 40 years, neither one of these languages have emerged as the sort of the dominant language. I used to teach this class in VHDL, and I switched to Verilog because I started to see this trend where VHDL is more common in university research, and Verilog is more common in industry. So if you guys go out and get a job at Texas Instruments or Cadence or Apple, and you're doing hardware design, you're probably going to be using Verilog, most likely. And if the only way you're going to see VHDL is if you become a professor. So I switched to Verilog, and I like Verilog. I like the syntax of Verilog a little bit more. I don't like all the typing. We used to use VHDL when I used the capture tool I talked to you guys about, where you would draw schematics graphically and it would generate the code. That was VHDL. But when it was like, well, I don't want to have them use the training wheels stuff anymore, we want to write code, and then I'm like, man, it's going to take forever to write the VHDL code. There's so much typing you got to do. If it's not generated by a tool and you're typing it in a text editor, it's too much. So I switched to Verilog. But they're both very similar. If you know one, you can learn the other one easily. Both of them are evolving, though. And so one of the things that happened recently is Verilog transitioned into SystemVerilog. And so Verilog had some idiosyncrasies to it, which were hard to teach. And SystemVerilog was designed to fix some of those idiosyncrasies, but it was also designed to extend the ability to write code that was for modeling. If you want to create models that are not intended to be synthesized, but just used for simulation, models like fake mock-ups of stuff that you can write at a high level, SystemVerilog brought in more power on that end as well. You guys with me? So what I'm saying is sometimes you write code that you intend to convert to hardware, and sometimes you write code that you just want to simulate. And SystemVerilog has more of the simulation stuff built in. So in this class, starting this semester, I decided to switch the language again from Verilog to SystemVerilog, because SystemVerilog, I think it's nicer, but it's new for me. So there may be a couple hiccups related to transitioning from Verilog to SystemVerilog, and if that happens, I apologize in advance, and we'll do our best to fix those. Yes.
Yeah. Just on that note, I was going to ask if there's any downsides to using SystemVerilog over Verilog.
The only downside is, and the reason I resisted for years to switch, was because a lot of legacy code's written in Verilog, and so I was teaching Verilog because if you guys go out and get a job and you have to look at code that was written in Verilog, it would be good for you to understand the idiosyncrasies of it. But the textbook switched from Verilog to SystemVerilog, and there's something, I got sick of dealing with some of the problems, and I'll mention what some of those are specifically as we go through. But not really, they're very similar. And if you know one, you can always learn the other one pretty easily. The hardest part of HDL is not the syntax. The hardest part is the fact that HDL uses concurrent semantics, meaning that every line of code operates concurrently. There's no ordering to the lines, right? That's the biggest. Once you understand concurrent semantics, as opposed to sequential semantics, which is what you've learned up till now, then picking up new HDLs isn't too bad. By the way, there's HDLs come and go. There's like, MIT came out with one called Blue Spec about 10 years ago. Oh, everyone's going to switch to Blue Spec, and then no one did. It disappeared. And now the big one is from Berkeley. It's called Chisel. And everyone thinks that Chisel is going to replace these. Chisel is based on Haskell. But Chisel might, oh no, I'm sorry, not Haskell, Scala. But I think Scala is based on Haskell. Anyway, there's kind of trendy ones that come and go, but these two are the ones that persist. But like I said, they evolve. Okay, so I mentioned we've got simulation and synthesis. These are two parallel roads that you take from a design. You write something in Verilog, and then you either go down the path of simulation, which is essentially where you're testing your design, see if it works. It's the debug. It's for debugging. And then there's synthesis, where you put it in the hardware. The underlying concept here is that once you put your design on the hardware, you can't really debug it. That's kind of the assumption here, the underlying assumption of this, right? Now you can debug it, but it's very painful and awful, because when you take your code and you convert it to hardware through synthesis, it takes a long time. It's a very time-consuming process. And you might say, well, come on, computers get faster I mean, it's got to be fast by now. No, it never got fast. Because, Moore's law makes computers faster, but Moore's law also makes the designs that you're synthesizing larger scale at the same rate. So you don't get any benefit. So it takes a long time to synthesize. And then once you synthesize, the problem is visibility. I mentioned, logic circuits have those internal signals, right? You can't look at, once you put your design on a chip, you can't look at the internal signals anymore. You can only see the top level inputs and outputs. So that makes it hard to debug. But if you simulate, you can look at all the internal signals you want, because they're all being simulated. They're all virtual. So you can drill down into your design and see what's going on under the hood. But once you put it into hardware, it's sort of closed off. Now there's a way you can put probes, JTAG probes in, boundary scan probes, but every time you add more probes, you have to resynthesize, and it's not practical to do. Now, that being said, the first lab, you're not going to be doing any simulation. We're going to go straight to synthesis. Part of the reason for that is I want you to experience synthesis to kind of show you why we want to be able to simulate. It's kind of a trial by fire. So you're going to write designs and you're going to go straight to the FPGA without any ability to simulate. And if there's a problem with your design, you're going to have to try to fix it on the hardware. But don't worry, it's going to be a simple design, and we're going to give you most of it. But in the second lab, you're going to be doing simulation, okay, just to kind of prepare you for that. Okay. Now, last lecture I mentioned design hierarchy. Which time do I have? Oh, I better speed up here. So design hierarchy. So designs are hierarchical. You have abstract modules, and then as you drill down, the modules are made from other modules, and those modules are made from other modules, and those modules are made from other modules, until you get down to just logic gates, which are kind of the leaves in the design tree, right? The most primitive thing you can get is a logic gate. Those are at the bottom of the design hierarchy, but at the top you have very abstract things like, processors, right? In SystemVerilog, the module is the unit of hierarchy. It is the unit of abstraction. So every time you create a design, you can build designs from the bottom up or from the top down, but every time you build something, you're building modules, right? So everything starts with every file has a module, and the first line of every file is module. Modules can be behavioral or structural. Behavioral means that you're writing code that is supposed to be translated into Boolean logic or into like state machines. Whereas structural is building a schematic, right? Now I mentioned that you can do schematics in VHDL. It's in text, but you can describe schematics being modules that are connected. You can also describe Boolean logic, right? And that's the difference between behavioral and structural. So I'm going to fast forward here a bit. So here's an example, called example, module example. So the first line is module, and the first thing you see here is the inputs and outputs. Up here at the top, then you have end module, and then everything in between is what's inside the module. This module has one line of code that says assign y equals tilde a, that means complement a, and tilde b and tilde c, so not a and not b and not c. Bar, which is the or, so the syntax kind of looks like Java. Ands are and gates, and logical ands. Well, I shouldn't say logical ands, bitwise ands. There's a bits. Bar is like an or, right? Bitwise or. So this is literally just a Boolean expression. So y is being assigned as a Boolean function of a, b, and c. You guys with me? Yes.
So is all that reading from left to right?
Yep.
Group the not a and not b and not c.
Well, there is an operator precedence. So the ands have precedence over the ors. So all the ands will be evaluated first, and then the ors. So this is a sum of products. Okay. Now, did I skip the? Yeah, let me come to here. Okay, so a couple quick things. Verilog is case sensitive, like Java and C, so you guys are used to that. You might say every language is case sensitive, right? No, VHDL is not. VHDL is case insensitive. That's why we bring this up. Names can't start with numbers, white space is ignored, and comments are the same format, luckily, as Java and C. Same comments. White space is ignored, though. This is significant because people have different styles for formatting their Verilog, especially when it comes to this part. Because modules very often have lots of inputs and outputs. So notice what I did here is I've got input ABC, comma, output Y. So I put the inputs and the outputs on different lines. But maybe not most, a lot of people like to put each one of these on their own line. And furthermore, they like to line up the input, the names, like tab things out, right? You guys will adopt your own style. This is a kind of a horrible style. Actually, this is hard to read the way it's written, but I was trying to, actually I think this came from the book slide originally, but the intent was to squeeze it into a little piece. But you'll notice when you read code, most code is spread out more, especially with these, these input and output lists, okay? So that's actually kind of hard to read. Also, these are pins, these are ports, input and output ports for the module. And notice that A is specified as an input and Y is specified as an output, but what about B and C? Why is it vague? Well, it's because B and C are inputs because the most recent specifier was input, right? Right? So it's implied that A, B, and C are all inputs because B and C are unspecified, so they're assumed to be inputs. You can say input before each of these if you want, and that would be another way to make it more easily readable and verbose. Yes?
Can you put more inputs after the output?
Yeah, in fact, the order doesn't matter at all. You can scramble them. Okay. I'm going to skip this just because we're running out of time here. Okay, so here's an example of, this is an example of how you declare a module. So here's a module that I've declared. And this is an example of how I would instantiate that module. So each module is going to be in its own file. That's the convention. So this would be in a file called and3.sv. The extension is sv, SystemVerilog. So I would create that module, and then if I wanted to use that module, it's actually kind of similar to creating an object in Java. You put and3 first, because that defines the type of module you want to instantiate. and then you give it a name, AND gate. Now this is the weird thing about this though. That name is irrelevant because you're building schematics. So you create modules and you connect them together with wires, right? Using these connections, using through the pin mappings, through the pins, right? The name is irrelevant. You never reference anything by name, modules by name. The only reason this name is here is in the simulator. It shows up in the simulator. When you simulate, you'll see the AND gate in the simulation. The simulator will show you the design hierarchy. But when you synthesize your design, it gets flattened. There's no hierarchy in real life. That's all just a concept, right? There's no hierarchy because ultimately when you synthesize it, it gets converted to a big rat's nest of wires and gates, wires and LUTs on the actual chip. So all of the naming and separating of things in a module kind of disappears when you synthesize it, but when you simulate it, you can see it. But even in simulation, you very rarely will even refer back to this name. So it doesn't really matter what you name anything, which is kind of funny, but you still have to give it a name. So AND3 AND gate has to be a unique name. And then this is the port map. So these are the inputs and outputs of the module. This is the port map, and this is how I connect. I put the dot A refers to A here, and then A refers to the signal inside here I want to connect to that input. Right? Now notice I deliberately put these in a different order. I gave Y, I connected the Y output first, and then I connected the B input second. The order doesn't matter. This is associating names here with internal signals inside the scope that I'm instantiating it. Yes?
So all the stuff in parentheses is like, we could read that like arguments to a function.
Right, yeah, these are like the formal arguments and these are the actual well, formal is the dot, which refers to this list, and the actual is here. I don't like calling them arguments. I mean, that's what they are, but they're really they're pins and ports and mappings. Yes?
Okay. Are there any kind of like predefined like functions or data structures? Like, for example, say it was Java we were working like, and they had like pre-built like lists. Like, do we actually kind of
Do we get pre-built modules?
No, well, you'll get them from like, generally when you do designs, you'll have a library of modules that other people have designed, but there's nothing built into the language, no.
But are we allowed to use some of these pre-built modules?
Good question. We've never had anyone try that before. Generally in this class, the designs are pretty simple, and we expect that you're building everything from scratch. Not because it's not like you're going to be building, the next Apple processor from scratch. Obviously, they have stuff infrastructure that they're building on top of, but we want to teach you guys the basics, so we kind of follow a bottom-up approach in this class, where we build a very simple thing, and then we build up until you have a processor. So we don't assume that there's any kind of pre-existing library. Okay, so right, so you've got here's a module AND3. This is a module, an inverter module. And then this is a NAND module, which takes an AND, it instantiates as AND gate, an inverter, and it connects, it has this logic N1, which is an internal wire that I've declared, right? Okay, so I write these two modules, then I create a third module with input ABC and output Y. So that gives me the ABC and the Y, right? And then I instantiate, and there's there's an N1, which is internal wire, which I declare as logic. And then I create the AND gate and the inverter by virtue of declaring them or instantiating them, right? And then the way that I have the mappings here, so notice that the input on the NAND is A, and the AND gate also has an input that just happens to also be called A. So I say, I want to take this A and I want to connect it to that A, and I do it with that, which does that. So this A gets connected to that A, that B gets connected to that B, and that C gets connected to that C. But the Y is going to connect it to N1, because N1 is the signal internally. So that's why you've got dot Y connected to N1, right? And likewise with the inverter, I've got an input A that I want to connect. I'm going to connect this N1 also to this input A. And I want to connect his Y to my Y. Like that. So that's why you have dot A, N1, dot Y, Y, right? Everyone see that? So these would be in 3 different files. Now, it's not going to be common that you're going to have such a small module, because you can actually you could just take these assignment statements, and you could just put them inside this NAND, right? And then you wouldn't have to. In other words, this is introducing a gratuitous amount of hierarchy, right? Generally speaking, your modules will be longer than just one line. Question?
Yeah, why do modules go in their end file?
I don't know. It's a convention. I think I remember I tried once to put multiple modules in one file, and I think I'm trying to remember. I think ModelSim allowed me to do that, but Quartus didn't, or some tools enforce that, other ones don't. But it's really just a convention. Okay, so this is a screenshot of a simulation. Now, this is notice a simulation is a waveform. So the inputs and the outputs are shown on the waveform, and this is a plot where the x-axis is time and the y-axis is the signals. Yes.
Can you perturb the inputs?
Yes, yeah, you can. So you can drive the inputs in the simulator. It's not the way you're supposed to do it. You're supposed to create a test bench, which which we're going to do in the next lab. That's why we're going to wait till we're going to do. Usually in a simulation, you have a test bench, which is another Verilog module that actually is in charge of driving the inputs and checking the output correctness. But in this case, this simulation was me just manually setting these guys, and then watching the circuit drive the output in response. So if you notice, A, B, and C are square waves, but the period of A is twice that of B, and B is twice that of C. So if you look at any moment in time, you get a counting sequence, right? So this is 0, 0, 0 for A, B, and C, and then 0, 0, 1, right, where C is 1, right? So this is like, if you look at A, B, and C as a number, where A is the most significant bit and C is the least significant bit, then you end up with this, it's just counting from 0 to 7. Right, and then repeating, which that's 1, 1, 1 right there. So by the time I get to this point, it resets back to 0. It rolls back over to 0, right? So actually, this simulation is run too long, because by this point, I've already gone through all 8 inputs. So it's just running in a loop. Okay, you can also do multi-bit signals. So the only thing you have to do to extend anything from 1 bit to multiple bits is use this bracket notation. Now this is a little weird. I don't know why Verilog does this way. There's 2 problems, well, not problems, but 2 things about Verilog multi-bit signals that make it different from an array in Java. The first is that the size goes before the name. So input number A, meaning A is a 4-bit signal. And also, for whatever reason, I've never been able to figure this out, but you have to give it the range 3:0, which means I want to create a 4-bit input A, 3:0. Why not just put 4 there? Yes?
Could you do something dumb like 8:4 and get
I-
another 4-bitter?
I think you can, but I've never seen.
That would be a perverse thing
Yeah.
to do, but
I don't know why anyone would want to do it, but I've never even tried it.
Does it matter which way you put the numbers in? 0, 3.
No, you can put it the other way, but I thought once that if you did that, it would reverse the order of the bits. It doesn't. So you can put 0:3, and some people actually do that, but it makes no difference.
so basically pick a convention and stick with it.
Yeah.
Okay.
Yep. So now this is another thing you'll notice. In this design, I've got 5 of these assignment statements, and crap, I'm almost out of time. Look at that, 5:25. for 35. Oh, good. Thank you. I forgot about that. Yeah, good. So we've got 5 assignment statements, and they're all operating concurrently in here. So the order that I put these assignment statements in this module has no effect on the behavior of this code or what hardware it will generate. Why? Because each one of these assignment statements represents a logic circuit. And all the logic circuits are operating concurrently. So anytime any of the values on the right-hand side change, the left-hand side value is updated immediately. Right? Make sense? So there's no notion of where I am in the program here. There's no program counter. There's no line of code that's currently being executed. All of these lines of code are always. By the way, I say concurrent assignment statement. In VHDL, it's called concurrent assignment statement. In Verilog, it's called a continuous assignment statement, but it's the same thing. It's basically just assigning a value to a input into an output or to an internal signal. You guys with me? Okay, and then you notice that there's binary values associated with each of these guys. So in this case, A and B are the inputs, and then I've got Y1 through Y5 are the outputs. Now in the waveform, it's not clear what's an input or an output, which kind of stinks. But yeah, there's really no way to tell just looking at the waveform. You have to look at the code and see that, oh, A and B are being driven by somebody else. And this code, the purpose of this simulation is to check to see if, based on the value of A and B, if the values of Y1 through Y5 are being set correctly by this module. That's the reason I'm simulating it, right? And then, by the way, this is the synthesized circuit. In lab, you guys are gonna, Charles and Rasha are gonna show you how to actually get this circuit from that code. So you put that code into Quartus, and it will actually give you that circuit. It'll generate this. This is a synthesized circuit. No one actually drew this circuit. This was systematically generated. Okay, so here's another statement that's common, is the ternary operator. The ternary operator actually is available in Java and C, although you guys might not have ever used it. It's a question mark. So you have a condition followed by question mark, followed by what the statement evaluates to if the condition before the question mark is true, colon, what the statement evaluates to if the condition was false. So this is how you can build multiplexers in Verilog really easily. You say S question mark D1 colon D2. That will take D1 and set it, well, this whole thing will evaluate to D1 if S is true, and then assign that to Y, right? And if S is false, it'll evaluate this expression, this ternary expression, to D0 and assign that to Y, right? So this is a one-line multiplexer. And this, you're going to have lots of these in your code because these are how, like I said, this is how you kind of steer data around at runtime in hardware. Yes?
Does Verilog have any kind of a macro language? Because I can see
Yes.
generating like a mux2, a mux3, a mux5.
I think so, yeah. You can do, there's actually a .vh header, they have header files.
Okay.
And there's a, instead of pound, like in C and Java, it uses a backtick. So there's a backtick define in Java. And I've never used it. I've never used it personally that I can remember. But yeah, you can do macros, sure. Okay, let's see, internal signals. I showed you this before, but if you have internal signals, you declare them with logic. Now this is one of the differences, by the way, between Verilog and SystemVerilog. Without going into too much detail, Verilog had two ways you could declare internal signals, as a wire or as a reg, depending on how you set them. SystemVerilog made everything logic. Okay, so logic is the only data type we're going to use in this class, is logic. Okay, so logic is just bits. Now bits, when I say bits, that means that the bits can be 0 or 1 or X or Z, as I mentioned earlier, right? X or Z are those two special values as well. Any questions? So what's going on in there? I've got P and G, they're assigned here based as a function of just the inputs, and then the outputs are assigned as a function of P and G. Right? So there's internal signals that are used as internal wires. Yes?
I heard that Verilog isn't like sequential, like everything happens at once.
Mm-hmm.
How can you assign to something that's happening to G right there?
So the G, so you've got this guy sets Z, and then this line this line sets G, and this line uses G, so it's on the left-hand side here, it's on the right-hand side here. So what will happen is if A or B changes, that'll trigger this line to update G. The update of G will automatically then trigger this line. So it's almost as if this circuit has a wire coming out of this line of code and feeding into this line of code. So they're sequentially connected, essentially. They're two circuits where an output from one circuit is being fed into another. When you simulate, these create event lists. So anything here triggers that, and then this changing G will trigger that line. So everything is based on triggers. Everything's based on triggers. If any of my inputs change, it triggers the output to be updated. So instead of statements being executed in program order as you have in Java, it's all based on triggers. Any inputs change, it triggers that line of code to execute, and it executes immediately.
See out at the top there, and the same thing would happen.
Sure, you can scramble these lines of code. It won't make any difference. The only exception to that is the declaration of P and G, which is kind of weird, but makes sense. I mean, you would want to put P and G, declare them before you use them in the code, right? Same thing with Java and C. But you don't have to declare them at the top, but they have to be declared before you use them. But the lines of code that actually do something, they can be scrambled. Okay, operator precedence. These are all the operators. I'm going to blow past this because we're running out of time. The next thing is numbers. So if you have a number, the way you represent it, and this is something that's easy to get into a bad habit, you're supposed to put the number of bits, whenever you have a scalar constant, you put the number of bits, apostrophe, then a letter that defines what base you're in, which is binary, decimal, or hexadecimal, and then the number. So for instance, if I have a 5-bit number, I put 5 apostrophe. Then I can put D and put 2. That will give me a 5-bit number with the value of 2, decimal number 2, which is going to be 00010. Right? If I change that to, I could put hexadecimal, or there's octal as well. You can do octal. I never use octal though. I don't know why they have. Octal is just grouping, by 3 bits at a time instead of 4 bits, but hexadecimal is much more common. So you could put like F, right? In which case that would be 0, 1, 1, 1, 1. So it would be a 5-bit value. You'd have a leading 0, and then 4 ones for the F, right? So binary, there's a 3-bit signal with a 1, 0, 1. If you don't put the leading number that defines the width, the default is 32. Now, if you assign that to, like, say, a 5-bit signal, then it will truncate the bits that don't fit. But it's best to, always specify whenever you have a constant to put in the width. Okay. Okay, I'm going to skip over this stuff. There's one more thing I want to mention before we got about a minute left.
Does the provider warn you if you truncate things?
Yes. Yeah, you'll get warnings. The problem is that there's a lot of warnings that not only warnings but info messages that come out. Okay. Actually, okay, I'm going to mention one more thing, and I'm going to come to lab. I'm going to do a brief lecture in the labs to try to just to fill in some of the things I didn't get to that you're going to need for the first lab. One of the things is this always statement. So the assignment, you might have thought, well, so far I've showed you how to instantiate modules and connect wires to the inputs and outputs, and I showed you the assignment statement, the continuous assignment statement. But that's pretty simple. If you want to do something more complex, including if you want to do sequential logic, clock logic, you have to use this always statement. And we're going to give you code, that you can try out with this. But basically, this always underscore FF pause edge clock will trigger on the rising edge of the clock. So this is a way to create a clocked statement. So in this case, I'm creating just a simple flip-flop that every time there's a positive edge or rising edge of the clock, I'm going to take D, the input, and I'm going to put it in a Q, and this will create a flip-flop, right? So this will essentially create like a delay element or like a register that I can put in, right? So in the lab, we're going to have you create this. This is the kind of the hello world design for the FPGA. This thing has two of these always statements. The first one does nothing but count. And the reason we're doing this counter is to create a clock divider, because we want to have the board flash a light, but the clock runs at 50 megahertz. And so if we flash the right light 50 million times per second, you can't even perceive that. But by putting a counter that counts to 2 to the 24th power, 16 million, and only toggling the clock 1 every 16 million ticks, you slow it down, to 50 divided by 16 hertz, right? And then we use that clock signal to trigger another always that will add 1 to this counter, which will go out. Well, this is actually the counter design. There's another version of this, slightly different, that does a shift operation instead, that will take a light and it will shift the light left and right on the FPGA board back and forth. Right, like a little, we call it a comet, but it's just a light that kind of goes back and forth. But this will show you kind of like how to set up the project and synthesize it. But I'll be in class on Tuesday and Wednesday with Charles and Rasha, and we'll finish out a few more slides, and then we'll get started in the lab. Make sure you email me. Oh, the other thing for my email that I forgot to mention at the beginning of class, email me your partner names. Right away. If you don't know who you want to partner with, then let me know, and we'll have a list, and we can assign you a partner. Okay? Thank you.